All right, so get this. We're diving into data science today. Um, Clustering algorithms, to be exact.
Oh, cool.
Yeah, you sit over this PhD thesis by Ji Yang.
Yeah.
It's amazing it's not just some, like, dry academic paper.
Right.
It's got some really innovative ideas that I think could really change how we analyze data.
It really is. And what struck me was how Yang tackles some of the biggest headaches in clustering.
Oh, really?
Like, think about it. You have mountains of data, and you need to make sense of it all. You need to find meaningful patterns, group similar items together.
Uh-huh.
But a lot of the traditional clustering methods are clunky, they're computationally expensive, and they require tons of fine-tuning.
Yeah, it's like trying to organize a messy room, but you can only use one hand.
Exactly.
So it sounds like Yang's coming in to save the day.
Well, he's presenting some solutions.
With not one, not two, but 4 new algorithms.
That's right.
Designed to make clustering smarter and more efficient.
Mm-hmm.
We're talking TC, MCHC, PMNNC, and AULTC.
Yeah, quite a mouthful.
Yeah, but each one addresses specific challenges, right?
Yes, and the thesis starts by laying out those challenges, and it's like Yang is handing us a roadmap of where clustering needs to go.
Okay, so let's start with the challenges then.
Okay.
What are the major roadblocks that Yang identifies with existing clustering algorithms?
So the thesis highlights 3 primary issues.
Okay.
First, many existing algorithms are incredibly sensitive to parameter choices.
Oh, so you can be really careful.
Yeah, you tweak one little setting and your results can go haywire.
It's not set it and forget it.
No, you really have to be like a clustering whisperer to get it right.
Wow.
It becomes this trial and error process that can be super time consuming.
Oh, man. Okay, so that's the first one. What's the second big challenge?
The second issue is computational cost. Some of these algorithms are resource hogs.
Yeah.
They take forever to run, especially with massive data sets.
And time is money.
Exactly.
Especially if you're in a field where you need those insights, like, right away.
Absolutely. And the final challenge that Yang addresses is something called finding optimal view weights.
Optimal view weights. Okay.
This comes into play when you're dealing with multi-view data,
Okay.
which is essentially looking at the same object from different angles.
So, like, if you were describing an elephant,
Yeah.
but you could only touch, like, a leg or the trunk or the tail,
Yeah. Perfect analogy.
you get different information depending on what part you're looking at.
Exactly. And the trick is figuring out how much emphasis to put on each view.
To get the best result?
Yes, to get the most accurate clustering results.
Gotcha.
That's where optimal view weights come in.
Okay.
And it can be a really tricky puzzle to solve.
Okay, so we've got parameter sensitivity, computational cost, and those tricky view weights.
Mm-hmm.
So that brings us to solutions.
Okay.
And Yang's first algorithm is TC, or torque clustering.
Right.
And I love this. It's inspired by galaxy mergers.
Yeah.
Wait,
I know it sounds like something straight out of Star Wars.
to-
But when you think about it, the way galaxies merge driven by those gravitational forces is actually quite similar to how data points can be clustered.
Oh, that's interesting.
So walk us through this. How did Yang translate galaxy mergers into a clustering algorithm? It's surprisingly elegant.
Okay.
So picture each data point as a tiny galaxy.
Okay.
Initially, they're all separate clusters.
Uh-huh.
Then TC starts merging the closest clusters together
Based on their distance.
based on their distance and mass.
Okay.
And the mass represents the number of data points in a cluster.
Kind of like the gravitational pull.
Exactly. So clusters with more data points have a stronger pull and are more likely to merge with other clusters.
Okay, and so what I love about this is that TC doesn't rely on a bunch of preset parameters.
That's right.
It figures things out dynamically as it goes,
Mm-hmm.
which makes it much simpler to use
Much simpler.
and less prone to those parameter tuning headaches.
Yeah, definitely.
But the question is, does it actually work?
That's the really impressive part.
Okay.
The thesis shows that TC performs surprisingly well on a variety of data sets.
Like what?
From classifying handwritten digits, like recognizing the numbers 0 through 9,
Oh, wow.
to analyzing complex RNA sequences.
RNA sequences, that's amazing.
Yeah, it is.
That's a huge leap from recognizing handwritten numbers.
Yeah.
What makes TC so versatile?
It's the algorithm's ability to adapt to different types of data.
Okay.
It doesn't rely on specific features or assumptions about the data structure. Instead, it focuses on those fundamental forces of distance and mass,
Okay.
which are relevant across different domains.
It's like a universal language for clustering,
Exactly.
regardless of what kind of data you're looking at.
Uh-huh. And to make things even more user-friendly, Yang incorporated a visual tool called a decision graph.
Oh, a decision graph. What is that?
It's a visual representation of the clustering process
Okay.
that lets you see how TC is making decisions.
So I can actually see which clusters are merging together.
Exactly, and how they're forming larger groups.
Oh, cool.
It takes the guesswork out of interpreting the results.
Okay, so we've got this algorithm that's simple,
Yes.
effective, and comes with this handy visualization tool.
Mm-hmm.
But how does it deal with those multi-view challenges we talked about, like those elephants in the room?
That's where MCHC and PMNNC come in.
Okay, so give us a preview. What are these algorithms all about?
Well, these algorithms build on the foundation of TC
Okay.
to tackle multi-view data, which, as we discussed, is like looking at the same object from different angles.
Okay, so how do they handle that multiple perspective problem?
Well, MCHC is all about speed.
Okay.
It leverages this really clever technique called fusion distance matrices with extreme weights.
Whoa, fusion distance matrices with extreme weights.
Yes.
I need a little help with that one.
Of course. So remember those distance matrices? They
Yeah.
basically show you how far apart each data point is from every other data point.
Right?
MCHC takes these matrices, one for each view of the data, and cleverly combines them, giving more weight to the views that provide the most clear-cut separation between clusters.
So it's like a weighted average?
Yeah, but for distance matrices instead of numbers.
Oh, okay, I see.
And because of this approach, MCHC is incredibly fast.
Even when you've got those big complex data sets?
Yes, even then.
Okay, that's great, but does it sacrifice accuracy for speed?
Not at all.
Really?
Yang actually demonstrates that MCHC achieves both speed and accuracy by focusing on the most informative views and prioritizing the separation between clusters.
Okay, that's amazing.
It's a win-win.
It really is a win-win.
So that's MCHC. What about PMNNC?
Yeah, what's PMNNC's superpower?
PMNNC is the optimizer.
Okay.
It uses a technique called particle swarm optimization,
Uh-huh.
which is inspired by the way flocks of birds search for food.
I love that visual.
So each bird represents a potential solution, a set of view weights.
Okay.
They explore the data, communicating with each other,
Wow.
and gradually converging on the weights that give the best clustering results.
So they're working together as a team to find the optimal solution.
Precisely. It's a really powerful way to optimize view weights.
To get the most out of your data?
Yeah, and ensure that we're getting the most informative clustering from our multi-view data.
Okay, so we've got MCHC, the speedster, PMNNC, the optimizer.
Right.
Both sound like huge advancements for multi-view clustering.
They really are, and what's exciting is that the thesis provides concrete evidence.
Oh, good.
Yang tested these algorithms on diverse data sets,
Uh-huh.
and they consistently outperformed or matched many existing methods in terms of both accuracy and efficiency.
So not just in theory, it actually works.
It does.
That's awesome. Okay, so last but not least, we've got AUMLTC.
Yes.
Almost ultrametric learning using pseudo-labels of torque clustering.
That's a mouthful.
What is that one all about?
This one dives into a fundamental aspect of clustering the way we measure distances between data points.
Okay.
The distance metric you use is crucial because it determines how similar or dissimilar data points are considered to be.
It's like using the right measuring tape for the job.
Exactly. AUMLTC focuses on creating a distance metric that makes the data more cluster-friendly.
Okay.
It introduces a concept called ultrametric space.
Ultrametric space. Okay.
Think of it this way. In an ultrametric space, the way we measure distances is extra strict.
Okay.
A good example is a family tree.
Okay.
Siblings are closer to each other than they are to their cousins.
Right.
And everyone is equally distant from their common ancestor.
Okay, so AUMLTC is trying to make our data more like a family tree.
In a way, yes. It uses the initial cluster assignments generated by TC, those are the pseudo-labels, to learn an almost ultrametric distance metric.
Okay.
This new metric helps boost the performance of k-means clustering,
Oh, cool.
which is a very common clustering algorithm.
So it's like using those insights from TC to fine-tune our distance measuring stick?
Exactly.
And then we can make the data more organized for k-means.
It's all about prepping the data for a better clustering experience.
Wow, this is fascinating stuff, but my brain is starting to feel a little full.
Yeah.
Maybe it's time for like a little recap before I move on.
Yeah, that's a great idea.
We've covered a lot of ground already.
We have.
We started by exploring the challenges that Ji Yang tackles in their thesis parameter sensitivity, computational cost, the quest for those optimal view weights.
Right.
Then we dug into the 4 innovative algorithms TC, inspired by those galaxy mergers, elegantly clusters data without relying on a ton of preset parameters.
Yeah.
Then there's MCHC, the speed demon, swiftly combines distance matrices from different views to find the most informative perspectives.
Exactly.
PMNNC, the optimizer, uses a flock of databergs, particle swarm optimization,
Right.
to find the best view weights. And finally, AUNTC, the distance guru, uses TC's insights to create an almost ultrametric distance metric,
Yes.
making data more cluster-friendly.
It's a fantastic summary.
So-
And what's really remarkable is that all of these algorithms have demonstrated impressive results compared to existing methods across a variety of data sets.
That's what makes this thesis so groundbreaking.
Yeah.
It's not just theoretical.
Right.
It's actually showing us that these algorithms have the potential to change the way we analyze data across various fields.
Definitely.
But I think we've given our listener a lot to digest for now.
Yeah, we should probably stop here for now.
Okay, so we'll pick up our deep dive into this fascinating world of clustering algorithms next time.
Sounds good.
See you then.
All right.
Bye.
Welcome back. So last time we explored those innovative clustering algorithms in Ji Yang's PhD thesis, and I have to say I'm still blown away by that galaxy merger inspiration behind torque clustering. It's amazing how, seemingly unrelated concepts can lead to these brilliant solutions.
Yeah, it really shows the power of thinking outside the box, and that's something that really shines through in Yang's work. They've drawn inspiration from so many different fields to tackle these clustering challenges. Absolutely. And speaking of TC, there's this concept that I'd love to dig into a little deeper, the idea of torque itself.
Oh, yeah.
The thesis talks about calculating torque for connections between clusters. And I'm curious, how does that actually work, and why is it so important?
It's a great question. So remember, TC merges clusters based on their distance and mass, the number of data points they contain.
Right, right.
Torque is a measure that combines those two factors. It helps TC figure out which clusters are most likely to belong together.
So is it like a force that's pulling some clusters together while pushing others apart?
Yeah, you can think of it like a cosmic tug of war with torque determining the winners and losers.
Okay, I like that analogy.
Clusters with high torque values for their connection are more likely to merge, while those with low torque values remain separate.
Okay, I'm starting to see how this plays out, but how is torque actually calculated?
Right, so there's a specific formula.
Oh, okay.
It's based on the mass of the connection, which is the total number of data points involved, and the square of the distance between the clusters.
Okay.
Essentially, the higher the mass and the closer the clusters, the stronger the torque.
So it's not just about how close they are, the size of the clusters also matters.
Exactly. That's what makes TC so good at handling data sets with clusters of varying sizes and densities.
Okay.
Traditional hierarchical clustering methods often struggle with this.
Yeah.
But TC's torque-based approach provides a more nuanced and accurate way to group data points.
That's really impressive. It seems like Yang has really addressed those limitations head-on with this approach. But TC doesn't just blindly merge clusters based on the highest torque values, right?
You're right. It also looks for significant gaps in torque values, which Yang refers to as torque gaps.
Torque gaps, okay.
These gaps act as indicators. They signal natural boundaries between clusters.
So it's like looking for those drops in elevation when you're hiking in a mountain range.
Yeah, precisely.
Signaling the separation between peaks.
Exactly. Those torque gaps are crucial because they help TC avoid accidentally merging clusters that should remain distinct.
So it's adding that extra layer of intelligence to the merging process.
It is.
This is making so much more sense now. It's like we're peeling back the layers of this onion and seeing how elegant Yang's approach really is.
I'm glad you're finding it insightful. And remember, we've only just scratched the surface of TC.
I know.
We haven't even touched on the intricacies of MCHC, PMNNC, and AULTC yet.
It's exciting and a little overwhelming all at the same time.
It is like we're explorers charting uncharted territory.
I love that.
And each algorithm is a new landmark to discover.
Okay, so speaking of examples, I remember the thesis mentioning all these different data sets that Yang used to test the algorithms.
Yes.
Can you tell us more about those and why that variety is important?
Of course. So Yang wanted to make sure that their algorithms were versatile, that they could handle different types of data.
Right.
They tested them on data sets ranging from handwritten digits and face images.
Okay, very visual.
Yeah, to RNA sequences and even astronomical data.
Wow, that's quite a range.
It is.
It sounds like they were really putting these algorithms through the ringer to see how they performed under all these different conditions.
Exactly, and the results are really compelling.
Oh, good.
The thesis shows that TC, MCHC, PMNNC, and AUMLTC consistently outperform or match the performance of many existing clustering methods.
Across all those different data sets.
Across these diverse data sets, yes.
That's amazing. It really speaks to their robustness and adaptability.
It does.
But how did Yang actually evaluate the performance of these algorithms? Was it purely based on accuracy, or were there other factors considered as well?
Accuracy is definitely important, but Yang also looked at efficiency, how quickly the algorithms could process the data, and robustness, their ability to handle noisy or messy data sets.
Okay, makes sense.
For example, they compared the runtime of their algorithms to existing methods, and they found that TC, MCHC, and PMNNC can often cluster data significantly faster.
Oh, wow.
Sometimes even 10 times faster.
10 times faster. That's incredible.
That's crucial in today's data-driven world where time is often of the essence.
Totally. And what about robustness? How do they test for that?
So for robustness, Yang tested the algorithms on data sets with noise outliers and overlapping clusters.
Oh, wow. So they were really trying to trip them up.
Yeah, all those real-world scenarios that can really mess with traditional clustering methods.
I see. And how did they hold up?
They held up well. The results are very encouraging. These algorithms demonstrate resilience and adaptability.
Even when the data isn't perfect.
Even when faced with less than ideal data, it really speaks to their potential for real-world applications.
This deep dive is really showing why this thesis is such a significant contribution. Yang isn't just proposing these new algorithms.
Right.
They're actually demonstrating their effectiveness across so many different scenarios and showcasing their potential impact on all these different fields.
Precisely, this is groundbreaking work with implications for data analysis, pattern recognition, machine learning, so much more. It's really pushing the boundaries of what's possible with clustering.
This is also fascinating. It's like we've opened this treasure chest full of knowledge and insights, and we're just starting to go through it all. But before we overwhelm our listener any further,
Yeah.
maybe it's time to recap what we've learned so far in part 2.
Good idea. Let's take a moment to synthesize our exploration of TC.
Okay, so we started by digging deeper into that concept of torque and how it guides the cluster merging in TC. We learned that torque is a measure that combines the mass of the connection between clusters, the Foley number of data points, and the square of the distance between them. We also discovered that TC looks for those torque gaps to avoid merging clusters that should stay separate.
Right.
Then we explored those diverse data sets that Yang used to test the algorithms, highlighting how versatile they are and how effective they are across different types of data.
Yes.
And finally, we discussed the evaluation metrics that were used to assess the performance of the algorithms, focusing not just on accuracy, but also on efficiency and robustness.
That's an excellent summary, and remember, we've only just begun to explore the depths of this thesis.
I know there's so much more.
There's still much more to uncover as we dive into the remaining algorithms and their unique features and potential applications.
Well, I can't wait to dive back in. So we'll see you next time for part 3 of our deep dive into the world of clustering algorithms.
See you then.
All right, welcome back to our deep dive into Ji Yang's PhD thesis on clustering algorithms.
It's been quite a journey.
It really has. We've explored the challenges we saw that galaxy-inspired torque clustering.
Yeah.
And now it's time to look at those multi-view marvels.
Yes.
MCHC and PMNNC.
Multi-view data. It's a fascinating challenge.
It really is. It's like having a puzzle,
Mm-hmm.
but each side shows you a different clue.
It is like those optical illusions where you see different images depending on how you look at them.
Exactly. Multi-view data is kind of like that. It gives you all these unique perspectives that can help you understand something better.
If you can piece it all together.
Yeah, but that's the tough part with multi-view clustering, right?
Right. How do you combine those perspectives effectively?
It's like trying to describe an elephant.
Yeah.
But you can only feel its trunk or its tail or its legs.
Right. You get a more complete picture by combining all those different views.
Exactly. But how do you do that with data?
Well, that's where Yang and work really shines. MCHC and PMNNC offer two distinct but equally impressive strategies.
Okay, so let's start with MCHC. What's its secret weapon?
MCHC stands for Multi-View Adjacency Constrained Hierarchical Clustering.
Catchy.
And it's all about speed and precision. It uses a technique called fusion distance matrices with extreme weights.
Fusion distance matrices with extreme weights. Can we unpack that a little bit?
Of course. So imagine each view of your data as a separate map,
Okay.
showing the distances between all the points.
Right.
MCHC takes these maps and combines them intelligently.
Okay.
But here's the clever part. It gives more weight to the maps that show the clearest separation between potential clusters.
So it's focusing on the maps that are the most helpful.
Exactly. It's like MCHC is a cartographer.
Okay.
Studying different maps and highlighting the landmarks that reveal the most distinct regions.
Oh, that's a great way to put it.
By emphasizing those extreme differences, MCHC can quickly identify the most valuable perspectives and combine them efficiently.
So it's all about finding those really clear distinctions.
Yes, and the thesis actually shows that MCHC can be much faster than traditional methods, sometimes even 10 times faster.
10 times faster.
Yes.
Wow, that's incredible, especially when you're dealing with these huge data sets.
It's a game changer.
But does it sacrifice accuracy to be that fast?
Not at all. Yang also included something called adjacency constraints.
Adjacency constraints?
It means that MCHC only merges clusters if they're really close to each other in the multi-view space.
Oh, so it's like a double check.
It's a quality control check, making sure that we're not forcing puzzle pieces together that don't actually belong.
So it's fast and it's accurate. MCHC is pretty impressive.
It is. What about PMNNC?
Yeah, how does PMNNC tackle this multi-view puzzle?
PMNNC, which stands for PSO-based Multi-View Nearest Neighbor clustering takes a more exploratory approach.
Okay.
It uses particle swarm
Oh,
optimization.
yeah, like those flocks of birds searching for food.
Exactly. Each bird represents a possible set of view weights.
Okay.
Those parameters that determine how much emphasis to put on each perspective?
Right, right.
And these birds fly through the data landscape, evaluating different combinations of weights and communicating their findings.
So it's like a team effort to find the optimal solution.
Precisely, it's this collaborative search for the perfect blend of view weights.
And how do they know if they're on the right track?
So Yang created a special fitness function
Okay.
based on a new clustering validity index called MSTDI.
MSTDI.
It stands for Minimum Spanning Tree-Based Duns Index.
Gotcha.
It essentially tells the birds whether their current set of view weights is leading to well-defined and internally cohesive clusters.
So it's like giving the birds a map and a compass
Yeah, a way to make sure they're heading in the right direction.
towards the best clustering solution.
Exactly. This fitness function is really important because it prevents PMNNC from getting stuck with a solution that's not actually that good.
So it's making sure they find the best possible solution.
Precisely.
Wow, both MCHC and PMNNC, they each have their own strengths.
Right.
MCHC is all about speed and precision, while PMNNC is the optimizer, really carefully exploring the data to find that perfect balance of view weights.
It's amazing to see how Yang tackled this challenge from different angles.
It is a testament to their creativity, and this deep dive has really opened my eyes to just how powerful clustering algorithms can be.
I agree.
It's incredible to think about how they can be used to find hidden patterns, make predictions, understand data in new ways.
And Yang's research is really pushing the boundaries of this field, opening up so many exciting possibilities for the future.
It really is. It's like they've given us this whole new toolbox for understanding the world around us.
Exactly. Their work is an inspiration to keep innovating and to keep challenging the status quo.
Absolutely. Well, this has been a truly fascinating journey. I want to thank you for guiding us through this research.
It's been my pleasure.
And to our listeners out there, we encourage you to explore this world of clustering algorithms.
Yeah, there's so much to discover.
Who knows? Maybe you'll be the next one to revolutionize this field.
That would be amazing.
All right, that's it for this deep dive. We'll see you next time.
See you then, TTAC.